Hello everyone, welcome to this video. My name is Farshad Mohammadi. I'm a PhD candidate at the University of Utah, and today I will talk about our recent publication, Multidimensional Scenario Selection for Power System with Stochastic Failures. So let's start with a little of background. Unit commitment or stochastic unit commitment is a tool that is being used in power system to minimize the generation cost when the demand is predicted. Unfortunately, not all the factors that we need to solve this problem are known for sure, so we need to consider different sources of uncertainties. For example, fuel price or amount of generation through a wind farm. And more basically here, we want to consider the effect of hurricane, which gonna result in unplanned outages in the network. And because of the many number of outages, it's gonna apply some serious challenge to the problem when we want to solve it. So let's start with an example to show what's the challenge and how we want to solve it. Let's say a hurricane is predicted to hit a large network with more than 1,000 transmission lines, and it's going to create a failure chance for tens of those transmission lines. So let's say that we have 60 lines with failure chance, and we want to solve the problem for day ahead, so 24 hours. We need to consider all the possible combinations for outages of different lines at different times. The total number of possible combinations for this problem is going to be more than 10 to the power of 88. This is even more than total number of atoms that we have in the observable universe. So imagine that we're gonna spend a couple of seconds or even minutes to evaluate each of them. Obviously, it's not possible to evaluate all of them. So we need to create a method to select a few number of scenarios, a few number of possible futures, and use it as a best representation of the future. While there are some well-known methods to create scenario and select, none of them are especially designed for power system and during that kind of extreme conditions. That's why we created this method, and we call this multidimensional scenario selection method. And this method starts with two dimensions. The first one, which is time, and the second one, which is the failure chance. So we consider number of thresholds, number of values over here, based on how many scenarios we want to be in that final set. For each scenario, we have a threshold value here, and by comparing the failure chance and saying that, okay, whenever this failure chance is more than this threshold value, we consider this line as a certain failure at this time for this scenario. The same applies for the rest of the scenarios and lines. This way we can create a limited number of scenarios. But the main problem with that is that we are ignoring the very significant information, which is the electrical characteristic of the line. So one line can be more important than other one. So that way we add another dimension to the problem, and we call it the network feature. For a transmission line, network feature is a function of line capacity. It's a function of operation point predicted based on the predicted load, and also how much is the effect of that line outage on the rest of the network, which can be done based on the LODF concept or line outage distribution factor. This way we can add another dimension. The same way we can add another feature, and then by combining all of them into the one single space, we can create our final scenario space. So here for this example, the time axis is not shown, but we have the network feature and the failure feature. Each star represents one single uncertainty. And in the same way, when we want to create scenarios, we define a couple of thresholds on each axis, and then the intersection of those threshold values is going to represent scenarios for us. So for example here, when we want to create this S7, scenario 7, whenever the failure chance is more than this value, and the network feature is more than this value, we consider this as a certain failure. To prove the efficiency of our method, we compared it with a couple of other well-known methods. So business as usual, keeping all the units available, doesn't matter how much is the cost, robust optimization, fast forward selection for scenario selection. And as you can see, not only the average unserved load and hour generation is better with our method, but also the standard deviation is much lower, which means that we are going to see more accurate solution for the problem. So that was a very basic introduction to our project. If you want to learn more, you can scan this code here and go to my Google Scholar. And thank you for listening.